conference to be a part of. So today I'm going to tell you about our work at the University of Connecticut. And when starting out, I was very motivated in realizing larger optical forces and just taking things back to first principles. I ultimately want to reduce this slowing length and increase the solid angle available from a cryogenic buffer gas beam source. In its purest form, all I'm interested in doing is maximizing both the recoil velocity by choosing light species with short wavelength transitions and also short-lived excited states to both crank on these two factors. I want a high scattering rate and a very large recoil velocity. And with that in mind, we're following two separate avenues at UConn. The first is to ask the question, how good can I make this, or how large can I make this optical force? And for that line of work, this is our molecule of choice, aluminum chloride. That requires UV radiation at 261 nanometers, but this looks very much like strontium, as we heard a little bit like from Stefan earlier on. This is the main cycling transition, a singlet sigma to a singlet pi, and you can think about that very much like a 1s to 1p transition in an alkaline earth. The other avenue is to look at these properties and say, okay, can I use this large optical force to mitigate the effects of maybe a not so attractive species to work with in terms of optical cycling, but a species that is chemically relevant and maybe exciting. And in that avenue of work, our molecule of choice are CH radicals. Again, it's very light. We have a blue transition, a beautifully high recoil velocity, but the excited state is fairly long-lived, and already this reduced line width kind of weakens the impact of this large recoil velocity, but ultimately this, I hope, will scatter very much like strontium fluoride or ytterbium fluoride or something like that. So not beyond the realm of possibility. So let's kick off with aluminum chloride. We need light in the ultraviolet, and I want to stress that the saturation intensity goes as the line width. Okay, that's going to be a challenge, but it also goes as 1 over the wavelength cubed. Oh dear, that's not going to be ideal. So as you move into the UV, not only does it become more difficult to make this light, you need more of it if you want to saturate a strong transition. So this is a brief overview of our home-built design. We partnered up with Agile Optic a few years ago to make these cavity housings, but I want to stress this is not an off-the-shelf laser. You do have to build this yourself. So we take an ECDL, we put it through a fiber amplifier to produce 10 watts, and then have 2 cascaded doubling stages. This works very, very well. It's detailed in this Optics Express, and we can turn about 10 watts in the infrared to about 2 watts at the time of writing this publication. Typically in the lab, it's about 1 watt, and I would encourage anyone building one of these systems to just bake in that overhead so that on a day-to-day basis, you're not constantly tuning up this laser. We very rarely have to tune these cavities and regularly get 1 watt or more out of them. So we've been making more than 1 watt of ultraviolet radiation from our first laser for about 2 years with no sign of UV degradation. That was really the thing that was scaring us before we went down this avenue, but they look really quite robust, which is fortunate because we want to run these for many, many years. There's also a very nice relocking, an auto-locking procedure that we follow that means that these lasers just stay locked essentially until the ECDL becomes multi-mode, which can be multiple hours. So we started off, once we had our laser, to produce a beam of aluminum chloride. Here are some absorption traces from inside the cell and outside the cell. We typically produce about 10 to the 11 molecules per steradian per pulse in our target ground rotational state for optical cycling. And I really want to emphasize that us building the laser and then finding aluminum chloride so quickly really was thanks to us standing on Berger's shoulders. He told us about how to make aluminum chloride and also where the transition was, thanks to his earlier in-cell spectroscopy, and I'm really deeply grateful to him for that. So we can measure the rotational temperature. We have a cold beam, internally cold at about 1 Kelvin. And to measure the forward velocity, we've already seen that this transition has a large excited state hyperfine structure, so it's hard to interpret Doppler shifts. Instead, we looked at essentially density as a function of position downstream, firstly by absorption just outside the cell, and then via fluorescence about 1 meter further downstream, and just asked the question of what velocity profile do I have to convolve with this initial temporal density distribution to get this density distribution, and this is a technique that's been employed by Tanya's group as well. So this is our typical velocity distribution from a new target. This is particularly good. It does get faster as the targets age, but we have a peak velocity at about 100 meters per second. with about 10 to the 11 per steradian. Okay, so very briefly, this is our cycling transition. And rotationally, in these singlet sigma molecules, you want to operate on the Q branch. That is the transition where J is unchanged and moving from ground to excited state. Any Q line here is closed. We have an awful lot of hyperfine structure arising from coupling of the aluminum nuclear spin followed by the chlorine nuclear spin. So we get three manifolds from each J, each of which contains 4 hyperfine states. Fortunately, in the ground state, this is unresolved, so we can kind of squint our eyes and pretend that this doesn't exist. And when we got started with this work, the excited state hyperfine structure was unknown. So that was really somewhere we had to push on immediately to get to grips with the type of excited state structure we would need to work with to optically cycle. So we performed a good amount of spectroscopy in our molecular beam, mapping out the Q branch and mostly the R branch. And we now have a Hamiltonian, as Berger said, that reproduces this hyperfine structure to a reasonable degree. We have a manuscript in preparation on this avenue, this collaborative work. So the Q branch is where we optically cycle. So this is where we want to focus our time and energy. And if we look more closely at the Q branch, you can see, first of all, that it's incredibly compact. Now, as a room full of molecular laser coolers, you will know this is really good news, because this tells me that the rotational constants in both the ground and the excited state are about the same, meaning that I'm on the way to achieving very diagonal Frank Condon factors. You can gain some insight into the structure within this Q branch by just overlapping it with the various R branches here. That comes with a slight warning that here, comparing R to Q is a little dangerous because you're looking at opposite parity states for R transitions as opposed to Q transitions, but it should be good enough to get your foot in the door. Since this work, we've come up with another technique to try and isolate this Q1 transition. This is our gold-plated optical cycling transition that we want to work with. And the procedure is the following. So here is our Q spectra. We think this is Q3, Q2 is about here, and then Q1 we think is in this area. So these are the transitions that we're driving, and we've got this cascading staircase going up and up and up for Q3, Q4, Q5. So what we do is leverage the fact that in our molecular beam, about 30% of the molecules are in J equals 0. Now, there's no Q0 transition. Unfortunately, in terms of cycling, these molecules are lost to us. What we do is couple J equals 0 to J equals 1 with microwaves. This allows J equals 1 to have more population than for its optical cycling. And when we scan the procedure again with microwaves present, we detect more fluorescence only from Q1, Q2, Q3, and so on and so forth are absolutely unchanged. It does also drop the scattering rate, but there are so many levels here at play that it only drops the maximum scattering rate by about 15%. So we've maybe doubled the number of molecules we can work with for a pretty small decrease in scattering rate. We can then take the difference between these two features and really get a close look for the first time at what Q1 is actually all about. So this is the excited state structure that we actually want to work with in terms of cycling. And a natural comparison is to compare Q1 to R0, which probes the opposite parity excited J equals 1 state. And these look largely the same, but I think this will be useful. These little differences will be useful as we refine our Hamiltonian and include lambda doubling. Okay, so we've heard before that this large excited state hyperfine structure is attractive because it enables potentially white light slowing. So I've got a spread here of about 500 megahertz at 261 nanometers. That's equivalent to about 130 meters per second. But I'm keen to stress that this structure is in the excited state. So when you now slow, you do have white light slowing, but in contrast to doublet sigma molecules, now every milliwatt that you apply gets to work for you, slowing every velocity that is in this spread. So if I couple light here, I'm slowing potentially very slow molecules on this F1 equals 3 halves peak, while also slowing very fast molecules, or molecules at about 130 meters per second, for this F1 equals 7 halves peak. So this structure looks very, very promising just for naturally slowing the molecule. And we also have anecdotal evidence that this large spread is very much like, you can think of it like an alkali atom. where you couple your repump laser and your cycling laser to different hyperfine states here, you don't typically form a lambda system in those atoms. And we have, well, preliminary evidence that suggests the same. When we make a lambda system with aluminum chloride, we definitely don't see the scattering rate decrease by a factor of 2, or roughly a factor of 2 from gamma over 2 to gamma over 3. That's very exciting from my point of view. You could also think about driving multiple Q lines here and having a MOT that's a real cocktail of different rotational states, but we'll see what happens there. Adding the Zeeman interaction to our Hamiltonian reveals that the excited state G factors are rather small. This, coupled with the large line width, means you will need a sizable magnetic field gradient for our MOT, and we have some coils in development to actually realize this. So this is where we are today. We have 3 deep UV lasers. The first 2 produce about 1.5 watts. The second laser is tunable. It can be a second cycling laser, or it can drive our first repump transition. And then our third laser is a lower power laser for driving the V21 transition, purely at 265 nanometers. This is a nice feature, being able to have 2 cycling lasers parked at different frequencies. So we illuminate our molecular beam transversely upstream and then detect fluorescence on a CCD. And we see that as we ramp up the power, we have loss. That's not particularly new or exciting. I would say any molecule would do that. But the key question initially was, is rotational closure truly guaranteed on one of these Q transitions on Q1? So what we did was drive our Q branch here on this main peak, which drives Q1, Q2, Q3, maybe Q4, and then use our second UV laser, a high-power UV laser, to probe different R lines and look at the rotational state population with and without cycling and say, how has the rotational population changed? How has it changed here? How has it changed here? And we can do that. Unfortunately, we see that the J equals 0 population are completely ignorant. There's no Q0 transitions. This is great news. We were really worried about seeing populations increase, showing that rotational branching was taking population from J prime equals 1 and putting it in the ground state in another rotational state. We don't see any increase. We just see evidence of scattering. We see loss. We see the most loss, i.e. the most scattering, from J equals 1 on Q1. We see almost the same amount of loss on Q2, some loss on Q3, and a small amount of loss on Q4. So this is evidence when we park on this densely packed Q forest, we're scattering on multiple transitions. This loss corresponds to scattering more than 250 photons per molecule, and there is no evidence of mixed rotational states and the kind of delta J equals 2 transitions people have seen in thallium fluoride, and no evidence of parity mixing and delta J equals 1 decays. This is really good news. So similarly, now we can look at the vibrational structure. So we can deflect our molecular beam by pushing from the side and detecting about 1 meter downstream. And we can look at that deflection as a function of power. I do want to say that these measurements really rely on you understanding your imaging system very well to avoid any systematic effects. So we can do this, deflect our molecular beam, and look at this loss for deflected versus undeflected as a function of the number of photons scattered. This is a direct measurement of the vibrational branching ratio. You can imagine here we're tossing a very biased coin n number of times and just looking at the probability that remains. We know our interaction time from our beam size and our forward velocity, and that also allows us to estimate the scattering rate. But I want to stress this is a mean scattering rate for every Q transition that we're driving here. So for Q1, it's likely going to be higher than this, which is good news. So we can push, and we can then introduce one of our repump lasers downstream in between our push and our probe region and say, okay, let's now return molecules from V equals 1. How does that loss versus deflection look? And we can now look at the collective vibrational branching ratio once we've plugged that additional leak. Okay, so the difference here is going to be that loss from V prime equals 0 to V equals 1. And we have a third repump laser, and we've done that. And now we're really getting towards the limits of what we can achieve transverse on the molecular beam. We only have 50 scattered photons at our disposal for these types of deflection measurements. And we're essentially measuring something which is consistent with 1. So this was both very good news that aluminum chloride is excellent vibrationally, as predicted. But it's now time for us to move longitudinally to enable more photons to be scattered. So these are our vibrational branching ratios, a little different to the theoretical prediction which kind of attracted me to aluminum chloride maybe 5 years ago. The biggest difference is this 0.1 VBR, which is larger by about an order of magnitude. I want to stress that I'm calling this a lower limit because there could be other loss mechanisms here, such as photoionization, decay to the triplet pi state. So this is maybe a worst case scenario, but it's already looking rather good. We've now got up to, well, and maybe even beyond, 10 to the 3 scattered photons. So moving to longitudinal scattering, we took a baby step initially. We had our transverse laser still scattering molecules, and then we just took our repump laser and shone it counter-propagating with the molecular beam and said, hey, can we still return 70% of lost molecules with a single laser frequency? And we saw that as long as we detuned slightly to the red to account for the Doppler shift of our molecular beam, we could definitely do that. So this was evidence that a single frequency can account for all Doppler shifts, but this is the ground floor because we only need to scatter one photon to return that population. So this is a good start, but it's definitely not the green light that this white light slowing, this built-in white light slowing is going to work. Since then, we've also moved our cycling laser to be counter-propagating. So this is a fluorescent spectra that we get now when we scan the Q branch longitudinally. And again, we're driving all Q transitions here. Q3, Q4, Q5 are all going to be Doppler shifted down into this part of town. So to just try and get a good handle on what's going on for Q1, this is the transition that we're interested in, we again did our microwave trick, coupled in those J=0 molecules, and looked for the increase in fluorescence purely from Q1. So again, we can take the difference. Here is fluorescence transverse and longitudinally, purely from Q1, based on the difference of our fluorescence profiles with and without microwaves. And this sets the scene for the kind of frequency space we'll need to cover, and we slow our molecular beam and ultimately trap these molecules in a magneto-optical trap. So that's the story with aluminum chloride. Let me briefly introduce you to CH. So vibrationally, CH also looks wonderful. This is very exciting. But the fact that you go from a doublet pi state to a doublet delta state in the excited state, and this was pointed out by Ian Lane back in 2011, means that rotationally, CH is a real headache. From our target excited state, we can decay to at least 5 rotational states. This is not ideal, but you can think about this just in terms of, okay, so vibrationally you can relax, you just need more rotational repumps. And people do it with vibrational repumps all the time. Why can't we do the same thing with rotational repumps? So this is what we're planning on addressing. So the first thing that we had to do was calculate these rotational branching ratios. You can see that it's really a 3-horse race. These 3 lowest states are mostly what we care about, at least for initial experiments like deflection and things like that. These other 2 states will ultimately need to be addressed if we want to capture molecules in a MOT. But this is a relatively polar molecule, similar to aluminum chloride. And I just want to emphasize that because you have this lambda doublet structure, you can polarize a hydride, which is kind of a remarkable thing to think about doing by mixing rotational states, which aren't so far apart. For slowing the beam, we have the option of AC Stark deceleration. And I want to also flag up the bichromatic force. This looks phenomenally good for for CH, because you have a fairly large recoil velocity, so a large kick for every photon you scatter. You have a relatively long-lived lifetime, so you can potentially apply lots of kicks before spontaneous emission shows up and spoils the party. And this is kind of perfect territory for a double TISAF. So this is something that we want to investigate and could potentially be useful for slowing a molecular beam, well, provided we can realize enough intensity. So we make our CH radicals via laser ablation of a solid precursor. There are no gas lines into cryogenic sources in my lab other than helium. We typically produce about 10 to the 11 CH radicals within the cell, and this translates to a pretty puny beam. We make about 10 to the power of 9 molecules per steradian per pulse. So this is about 1% the brightness of our typical strontium fluoride or aluminum chloride beams. But it's CH. It's a relatively chemically relevant species, so we're happy to work with this. So we had to work relatively hard for this much absorption back several years ago. And I want to stress that when you're interpreting the number in your cell, for these long-lived excited states, you absolutely must account for collisional broadening. Otherwise, you could definitely overestimate the amount of molecules you actually are producing. Within the cell, we have a rotational temperature of about 2 Kelvin. It's really hard measuring the rotational temperature of a hydride. You either see stuff or you don't. And to just verify that we knew where this transition was, we increased the temperature of our cell, took under the rotational temperature, saw that line, and thought, OK, we know what we're doing here. Similarly, we can look at the forward velocity by measuring fluorescence at 2 points along the molecular beam line. And we see a forward velocity, again, peaked at about 100 meters per second. And I should stress that both of these sources are single-stage sources. So the scene is now set for optical cycling. We've recently upgraded our imaging region to give us better signal to noise, since we are working with such a weak beam. This is kind of a challenge. But we focused on producing CH in larger quantities to try and beef up this brightness. So we've improved our target making procedure, and we can make absorption profiles now that look more like this. And if I plot this on a log scale, so we would just expect 1/tau diffusion of our CH from our molecular beam. You can already see this doesn't really look like an exponential. And if I plot it on a log scale, you can see this is definitely not a straight line. To account for this profile, I need to include this second term, which accounts for two-body loss within our cryogenic cell. This is evidence of cold organic chemistry already happening at about 2 Kelvin or so within our cryogenic source. But this is cold chemistry, cold organic chemistry, not ultra-cold organic chemistry, but cold organic chemistry involving just a handful of quantum states, maybe years before we expected to see it. So we can analyze this plot, and we get a two-body loss rate coefficient, which is enormous, essentially, on the order of 10 to the power of -6 centimeters cubed per second. And this was very exciting, but also confusing. What is going on here? And the natural question is to ask, is this CH-CH? We can now say that it is not. We can now produce CH in greater quantities. And you would expect, if this is CH-CH, for this two-body loss rate coefficient to not care about how much CH you're producing. It should always be the same number. We see now when we make more CH, we actually suffer less two-body loss than we did before for this previous curve. This is showing this is not CH-CH, which kind of makes sense since we're using laser ablation and producing a cocktail of stuff. This is CH with some other invisible collisional partner that is produced at just the right density that it too will also decay essentially to zero and undergo this two-body loss process, but it's not CH. So what is it? That remains an open question, but if I had to describe this process, we're not really seeing this coefficient here. We're seeing this coefficient, and this is one of the drawbacks of absorption imaging. It's so species-specific that you're really not seeing the big picture. If I want to be naive, so I can say I've ruled out our 7 times 10 to the power of -7 two-body loss rate coefficient. Okay, it's about an order of magnitude less. Is this now CH-CH? And I don't know it isn't, but I know it probably isn't. If I'm going to be naive and say that this is now CH-CH, it wasn't before, but now this is CH-CH, we would come up with a two-body cross-section of 10 to the power of -11 or less. This is about an order of magnitude greater than sodium in a magneto-optical trap. But the real answer is here, we really don't know. We need to keep measuring these curves, keep pushing up the density to keep reducing this, this upper limit. Ultimately, absorption imaging is not the way to go here. We want to set up ion detection to take a look at really what's going on and what's coming out of our cell in our molecular beam as a function of CH density to really try and get a bigger picture on this cold organic chemistry. It's still cold organic chemistry. We still have two-body loss. It's just not CH-CH. And it's less chemistry than we saw earlier, let's say. So this is a summary of what I've talked to you about today. I've talked to you about our aluminum chloride experiment. We have 3 UV lasers giving us closure to at least 1,000 photons, hopefully more. We have RF Mach coils, not RF Mach coils, DC Mach coils now in construction. And I've talked to you about our work with CH. So let me just flag up the people that have done the work. This is our team on aluminum chloride. I really want to mention Jamie Shaw, who's now writing his thesis. He's been with me from the very beginning on this project and has really done, well, all of the work, I can say, in building the lasers and doing the spectroscopy. In the last year or so, he's been joined by Mark and Will, and now they take the reins of our aluminum chloride project. Before I close, I want to also flag up that at UConn, we're now searching for a tenure track faculty member, so please spread the word about this. At the moment, I'm the only laser cooler at UConn, the only ultra-cold physicist, which is something I'm not very happy about and hope to address soon. Okay, thanks a lot for listening. There's definitely, there are more hyperfine states. Yes, and there is, the hyperfine structure is definitely more involved. In the ground state, we don't care about that because it's still unresolved. But at the moment, I'm trying to leverage that into more of a feature than a bug, in that once we have these molecules cooled and trapped, we'll have this beautiful, intricate playground to explore with microwaves.
And
yeah.
Is there, like, why do you stop at the power? Why does it go even larger?
Then I'm kind of violating my rule of a low mass molecule. Chlorine was already a bit of a compromise. Yeah, I want as high a recoil velocity as possible. I want a short slowing distance to really push on this avenue and see how good can it possibly be. The fluoride is ideal, but I was perturbed by 227 nanometers, unlike Stefan.
For adjusting these rotational states, how do you actually plan on generating the light? I assume it's going to be separated by tens of gigahertz, so maybe not.
For trapping multiple rotational states?
You said you're going to be repumping the two rotational states?
Yes. So the rotational states themselves are separated by at least 15 gigahertz or more, but the transitions which we optically drive all fall essentially at the same frequency. They're all on this Q branch where you go up one rotational quanta in ground and excited state, and that increase is the same in ground and excited state approximately. So all of these transitions essentially switch on at the same wavelength.
Thanks, Dan. So molecules like calcium chloride, strontium chloride, strontium hydroxide, this is standard argument for why the vibrational branching ratios should be as good as they are, which is everyone else does. Is there something similar for these kinds of molecules?
This is a question I've flagged up a few times, and it's wild to me that you can promote an electron from a closed electron shell, and the molecule shrugs and says, yeah, okay, that's not going to affect my binding at all. I don't have a good rule book or a good understanding of how that is. I looked at tables of molecular constants and thought, oh, that seems to be the case. Okay, and it seems to be the case, but I wish I had that intuition. I would love to understand why. Yeah.
I have a question to this losses of bimolecular reactions. If you speak about CH-CH, what kind of molecule do you have in mind?
So we've been working with our theory collaborator at UConn, John Montgomery, and these are some Gaussian calculations that he did, where he looked at what happens with CH-CH, and the bottom line is it almost always produces acetylene, and he's encouraging us to fire up an IR laser and actually look for this in the cell, which would be wonderful to see. Well, one species disappears, the other shows up. With this now confirmation that it's not CH-CH, at least previously, I feel less motivated to look optically and to just set up the ion spectrometry to try and look at everything.
There's some approximate spin selection rule, I guess, right?
Yes, that's definitely true. And we've seen actually, so there's a quartet sigma state, an intermediate state. If you go into that state, you can actually stop this chemistry happening altogether. Yeah, we would love to try that. Yeah.